We all should be concerned about our monies in our bank accounts. Perhaps the most common way we access our monies are with credit debit cards. Unfortunately, others want our monies too, and illegally. Therefore, they often target credit debit cards as a way to get to our monies. Increasingly, we hear of machine learning and deep learning as part of the solution sets financial institutions are using to combat the difficult problem of credit card fraud. This video walks us through the credit card fraud problem and put in rather simple terms how machine learning can be applied to help solve the difficult problem. To do this, we will demonstrate machine learning in a real-world scenario. I am Dr. Michael Treasure, and for the next 15 or so minutes, I will first provide context. Second, I will look at the data. Third, I will build ML models and present the results. Fourth, and finally, I'll provide a summary and conclusion. A general internet search will shine light on the magnitude of the credit card fraud problem. In 2021, in the US, nearly 400,000 credit card fraud cases were reported. Imagine the number of unreported cases. The largest recorded credit card breach affected some 160 million accounts. In 2021, the global loss to credit card fraud was pegged at $32 billion. The loss globally for 2023 is projected to be over 36 billion US dollars. According to the online magazine Moneyzine, by 2024, about 74% of losses will be attributed to card not present fraud. Since 2015, credit card fraud has increased by 13.3%. The article referenced here about Jamaica talks about the rising BIN card fraud attacks that are on the rise in Jamaica. BIN, Bank Identification Number, is generally the first 4 to 6 digits of a card number that is assigned by the card network to a specific bank. The BIN not only identifies the bank, but it also identifies the card network. As the article speaks to, bad actors use computer programs to guess a 16-digit card number, as they only have to guess the last 12 numbers. Then they try the card number, combine with guesses for the corresponding CVV and expiry date for the card by executing several transactions to see which one goes through successfully. The machine learning model that will heretofore be demonstrated will use this BIN credit card fraud as the use case for the developed machine learning model. Before we go any further, let's establish some basics. Card not present, CNP, generally references transactions completed remotely. Card present, CP, generally references transactions done in person at retail point of sale. Card not present fraud is harder to detect and prevent than card present fraud. Card present fraud involves the use of counterfeit or stolen card at a point of sale. The BIN fraud attack reported in Jamaica case may have involved both card not present and card present. Also, for context, credit cards should be understood to mean both credit and debit cards. And the internet should be understood to mean internet, mobile, or over the phone. As shown here in the diagram, there are about 7 layers of stakeholders that make up the credit card ecosystem. Major stakeholders in this ecosystem are increasingly investing in various technologies to combat credit card losses. Two of the major technologies of increasing importance are artificial intelligence, AI, and machine learning, ML. Machine learning in credit card fraud problem solving has gotten the attention of many around the world, as shown here. In recent years, hundreds of papers have been written on the subject. Machine learning is the most prominently written about and increasingly being used with effectiveness. In attacking the credit card fraud problem, much attention has been on supervised machine learning. This is when the computer is taught to recognize something. It then does this on new data with incredible speed, consistency, and accuracy against large data sets. With the backdrop I have now provided, let's dive into how with an actual coded implementation. So, what exactly do we want the computer to tell us? Three things. First, we would like to know the probability of a transaction being fraudulent by categorizing the transaction as a 1 for fraudulent or 0 for not fraudulent. The second thing is we would like the computer to tell us the probability of a transaction being fraudulent, that is 1, or not fraudulent, 0, and categorized as done at retail point of sale or over the internet. And the third thing is to show other related features tied to transactions that are flagged as fraudulent, that is a 1, or not fraudulent, that is 0, and completed at retail point of sale or internet based upon the other features that we have looked at in terms of the database. Finally, our model will show then how these may help to identify and solve the bin breach problem that we talked about earlier. For our machine learning model, we need data, lots of it. Therefore, we're going to use a data set from Kaggle. Kaggle is owned by Google. It is an open community and has over 15 million machine learners sharing, stress testing, and staying up to date with the latest machine learning techniques and technologies. The particular dataset we're using from Kaggle is the Credit Card Fraud Detection Dataset 2023. This dataset contains credit card transactions made by European cardholders in the year 2023. It has over 550,000 records. That is, those are transactions, 550,000 transactions. The data has been anonymized to protect the cardholders' identities. Because the data set from Kaggle has been anonymized, we will need to get some help understanding the data set and getting additional data to achieve our 3 machine learning goals. For this, we're going to ask Google again. This time we'll ask Google's Bard to help with research data. Bard is a large language model built with AI and machine learning. The question we asked Bard was, what is the average number of credit card and debit card transactions for the average person in 2023? Bard came back with a detailed set of answers, as shown here. In one answer, Bard cited a study that said the average number of credit and debit card transactions per average person was 137 per month. 110 were with debit cards and 27 was with credit cards. The average transaction amount for debit card was $64 and for credit cards it was $116. These stats will become very useful to us later on in our machine learning model development. This is what the Kaggle dataset looks like in terms of schema and records. According to the dataset providers, V1 to V28 tells a lot about credit card transactions, users, card types, place of purchase, time of purchase, etc. But because of the anonymity, we do not have the details, nor do we have context of the data. We're going to do some form of reverse data engineering to the Kaggle dataset. In doing so, we will need three sets of additional information. One, customer profile consisting of a customer ID, location of a customer, average amount that the customer spends, the amount of each transaction, and the time. We also need as terminal profile consisting of the terminal ID, which is a unique identifier, the location of the terminal, and the payment mechanism, whether the transaction was done at a point of sale or it was done over the internet. And the third thing we need is the card profile, which is a card number, 16-digit number made up of two parts. The first 4 digits, which we call the BIN, representing the card network and bank card set, which is assigned by the network. And the last thing in the card profile, we need to combine 12 digits with those 4 digits to create the card number. Here we have now combined 4 different data sets to give us a more complete foundation for our machine learning model development and training. Going forward, for our purpose, we will replace the amount field from Kaggle dataset with our standard amount created data. However, we will maintain the scale, that is the ratio between maximums and mean, as well as the mode and mean. Based on the information we use from Google's BARD, we now have a basis for time, reflecting how long the 550,000 transactions would take if we had only 1,000 customers performing the transactions based on our calculated average transactions per day per customer. Now that we have done the prepping of our data, we can visualize the data. This shows a panoramic view of 42 plots representing the 42 features of the dataset that will be used to develop and train our machine learning model. Of the 42 plots mentioned earlier, I have focused on a few here. Note the following. The ratio of retail point of sale versus internet transaction reflects our ratio of 80% to 20% respectively. The standard amount is a weighted average between debit card and credit card transactions based on the Google BARD information of average transaction per customer per month equal 137, of which 110 are debit cards and 27 are credit cards. Finally, it's worth noting that the average purchase amount per customer with debit is $64 and for credit card is $116. The combination of those two gives us the weighted average, which is used to help us with deriving the standard amount. What is shown here is a correlation map of the 42 features. In the middle highlighted area of the map, we see a dense correlation between most of the features from the original Kaggle credit card fraud 2023 dataset. We can see there are varying correlations between features. Earlier, we did talk about this original dataset was transposed using principal component analysis, PCA. PCA is a method used in data analysis to reduce details but substantially maintain enough related information. I should also point out, although both the highlighted left and right areas of the map do not show a dense set of correlation, we cannot rule out that those features do not have a causation effect to fraudulent or non-fraudulent transactions. I will not be showing the technical under the hood details of the ML model developed and trained. You may read the accompanying white paper to get the technical details. Here, I show the results of one of the ML models developed. This ML model has done extremely well in determining whether a transaction was done at retail point of sale or over the internet. The metrics used to determine how good the ML model had performed are shown here. They show the accuracy of the predictions the ML model performed at. Here I show the results of one of the logistics ML models developed. Again, this ML model has done extremely well in determining whether a transaction was fraudulent or not. The metrics used to determine how good the ML model performed are shown. They show the performance and accuracy of the predictions of the ML model. I should point out here that the original Kaggle credit card fraud 2023 dataset contained practically equal quantities of class being 0 and class being 1. In the real world, this is extremely unlikely. In the real world, there would be a disproportionate class imbalance with far more non-fraudulent to fraudulent transactions. However, in a bin compromise case, as in this one we looked at, the imbalance may not be disproportionate. With the ML model, we can run automated queries to help us filter to flag and get answers as to the origin of the fraud, including identifying the time, place, and card used. Shown here is a query against a specific card number with the probability outcome of transactions being fraudulent or not, and the corresponding information on the terminal used for a transaction. It also shows whether the transaction was likely at retail, POS, or over the internet. Remember here, time is defined as the day of the transaction. What about setting up automated query investigations at the bin level? Here, from the ML model, we are looking at the bin 4850 with the highest to the lowest probability of the prediction for 30 transactions. If we look at the feature class, which is the target for fraudulent, and the prediction feature of the ML model, we can see the corresponding highest probabilities of the predictions against a complete set of cards for the queried bin. Here is a similar query as the one previously shown, but with the focus now on the other bin. In this query of the ML model, we are looking at the bin 5255 with the highest and lowest probability of the prediction for 30 transactions. Let's summarize and conclude our practical machine learning demonstration in helping to solve credit card fraud. In this video, first, I talked about the increased use of machine learning and the attention it is getting around the world in helping to solve the credit card fraud problem. Second, I presented a use case of a real-world problem highlighted in Jamaica regarding credit card fraud at the bin level. Third, I spoke about the data set used and the process in preparing the data set for the machine learning model to be developed to attack the credit card bin fraud problem. Fourth and finally, I presented the built machine learning model demonstrating its ability to be a potent tool to be used in helping to solve the credit card fraud problem. The conclusion is, with machine learning, we can confidently increase the probability of staying ahead of solving the credit card problem, no matter the nature. Thank you.